This is a screencast that's going to kind of explain the idea behind the proof of the mean value theorem. So you can reread the mean value theorem, but the whole idea is we're going to use Rolle's theorem. But Rolle's theorem only works if you have the endpoints being 0. And you don't necessarily know that here. So instead we're going to say, we're going to use it on this function, this mysterious function d of x, which equals f of x minus kind of a whole big long thing. Now the main point is, this whole long thing is the equation of the secant line. So if you go through and you think back to high school algebra, you'll see that this is just the equation of a line. Remember, a and b are constant. So the idea of the proof, I'm just going to give you a picture to kind of let you know what's going on. So the example is, I'm going to look at f of x equals negative x squared plus 7 on, how about, negative 2 comma 1. Alright, and the reason why I chose this is because it's going to kind of look like the picture in the book. But the graph of this, negative x squared plus 7, looks like it's an upside down parabola. Here's the point 0, 7. I'm going to label a couple of key points here. In fact, let's do that in green. Right, here's the point 0, 7. Here's the point, that's 1. So here you get the point 1, comma 6. Here you get the point negative 1, comma 6. And finally, we're going to look at the point negative 2, which you get the point negative 2, comma 3. Also, what's going to be important is I'm going to need to draw in the tangent line, the secant line, sorry, between these 2 points. I'm on negative 2, 1, so I'm going to start at negative 2, draw a line through 1. And again, go back to high school, this line is just x plus 5. Now, the important thing is I'm going to make a table here. The table, and then I'm going to graph something. The table, for an x values, I'm going to choose nice integer ones, negative 1, negative 2, 0, 1. Then I'm going to figure out what f of x is. I'm going to figure out what y equals x plus 5 is. And then d of x is just defined to be, right, f of x minus, in our case, x plus 5 is whatever the equation of the line is. That's what this d of x is. That's what it always is. So if you just plug in these values, I already figured these out, right? For f of x, the value is just 3, 6, 7, 6. That's it. 3, 6, 7, 6. Now, x plus 5, what happens here is I just add 5 to these. Negative 2 plus 5 gives me 3, gives me 4, gives me 5, gives me 6. Now the key thing here, d of x means just subtract these y values. So d of x, the y value of d of x at negative 2 is just going to be 0. 3 minus 3 equals 0. For at negative 1, you get 6 minus 4, which is 2. 7 minus 5, which is 2. 6 minus 6, which is 0. And notice in particular, at the endpoints negative 2, 1, now I get values of 0. So let me draw the graph of d of x. The graph of d of x, I'm just going to draw it on the same axes. The graph of d of x here is going to be, I can plot 0 there, 0 there, and then I get 2 there, which is like there, and like that. And if you actually did this for all the points, I think it'd look roughly like, look kind of parabolic. So now on this red function, I can apply Rolle's theorem. Right, so on Rolle's theorem, I can apply this, and then everything just works out kind of nicely. Right, I get d prime of c is equal to, d of b minus d of a over b minus a. But Rolle's theorem says that this is actually equal to 0. So if you go through the algebra, you can see that 0 equals db minus dA over b minus a implies this. So that's the idea, and here's an example. This is what you should think of. You want to just kind of basically look at the difference between these two, use Rolle's theorem on that, and you're set. Bye-bye.